Alright, so I am first going to derive the third-dimensional heat diffusion equation. Alright, so we first start with the cube on Cartesian coordinates x, y, and z. So this is delta x, delta y, delta z, with heat entering this way and exiting this way. And we label the left side position as qx and the right side position qx plus dx. Alright, so the volume of this cube is simply delta x times delta y times delta z. Right now, so the energy balance of this is the rate of energy accumulation is equal to the rate of net flow, heat flow, plus the rate of energy generated. Alright, so now we're going to define the variables. First, the rate of energy accumulated, which is density times the heat capacity times the volume times the partial derivative of temperature over distance. Alright. Now the rate of energy generated is simply the heat flow rate times the volume. Now for the rate of net heat flow, the rate of net heat flow is derived from two equations. The first, net heat flow, is equal to the first position minus the second position. The second equation, do I have enough room? Yeah, I do. Alright, so the second equation is the Taylor series of the second position. The Taylor series of the second position. So this is qx plus dx is equal to qx plus the partial derivative of q over x times dx. And then you combine these equations, and then you can cancel out qx, and then you get q net is equal negative partial derivative of q over x dx. Alright, so then you combine all of these equations. Alright. So yeah, we combined all these equations are in the energy balance, and we can apply Fourier's law, which is Q is equal to negative K A D over. Alright, and we apply that, so then we get All right. So this area here is delta y times delta x. We get that from this side, the area of that surface, because that's where everything is flowing through. So we can cancel out dv. All right. And now we can assume K is constant, so we can use the heat diffusivity equation. So then we get the second derivative of temperature over position plus Q over CP. All right, and that is so that equation is the three-dimensional heat diffusion equation. So the three-dimensional heat diffusion equation is the gradient of temperature over time equals heat diffusivity over the partial derivative of temperature over distance times Q dot over density times the heat capacity. So this part I'm going to go over first dimensional heat diffusion with one side being equal or perfectly insulated. So I draw this. So this side is perfectly insulated. Q dot K. And this has a length of L. This is x equals 0, so this is the positive direction. All right, so energy generation is equal to Q times the volume, which is length, times the area. And this is equal to K, Fourier's law K times the area over T x. And because this is going to the left is to the positive direction, Fourier's law says that heat flows in the opposite direction, so this is negative. This is negative. So then you can cancel out A. So the gradient is Q times L over K. Alright, and explain physically why the magnitude of the temperature gradient increases further from the insulated side. So as you are going away from x equals 0, the volume is increasing behind you. So as as the volume increases, that means there's also more heat generation. So if there's more heat generation, well, I guess let me backtrack a little bit. So this is what the gradient currently looks like. X equals 0 here because it's perfectly insulated. So the gradient looks something like this. And so the slope is steeper here than it is here, because as you are moving closer to the insulated side, there is no heat generation there. And as the volume increases, there's more heat generation. And with more heat generation, the steep has to be higher to remove that heat faster as the volume increases. This part I'm going to simplify the 1D energy or heat flow equation to a 2D heat, or heat diffusion to a 2D heat diffusion. So heat energy, we'll start with the energy balance. Energy storage is density times heat capacity times the volume, and then the heat flow. So we have to do this for each plane. So this is going to be derivative with respect to x, heat capacity, times partial derivative of temperature with respect to the x times the area, and the area is dy dx, dz. Then we have to do the y. The y plane. Temperature gradient, temperature with respect to y times the area, and the area of this is dx dz. And then we have to do the energy generation, which is Q over rho Cp. Alright. Then we can cancel out the velocity, or not the velocity, the volume, and we can do the Laplace of this equation, and this is alright. So this isn't the politically correct version. This is just like the dumbed down version, simple version. Now I'm going to do the very technical version. So alright, so now for like the politically correct version, so you can get like the exact values. So we're first going to start with the energy storage. Oh. So we're going to, this is like a coordinate system, like the two plane. And we're going to say that x is equal to I delta x, and then y is equal to j delta y, and then time is equal to n I j. And then we're also going to say that delta x is equal to delta y. So that's saying that they're just even little blocks. These are all even blocks, even though they don't look even. Okay, so the energy storage for this is going to be temperature n plus 1 ij plus t to the n ij over delta t, and this is equal, so we're first going to do the x side, so we'll do diffusivity, and this is equal delta x, and so I n is I plus 1 j plus tn ij minus delta x over t n ij plus tn I minus 1 j, and this is all over delta x. Alright, and now we're going to do the y. So this is tn I j plus 1 plus tn I j. Oh, this is over delta y. Plus tn I j tn I j minus 1 over delta y also, and this is all over delta y plus over CP. All right. So now we are going to simplify. So I'm going to bring this down. We're going to put this all over delta squared because x and y are equal. So we're going to bring this term down. Not working. Okay. Tn I plus 1 j plus T n I minus 1 j plus T n I j plus 1 plus I n over I don't know why I keep writing my j's like that. J minus 1 and this is all minus 4 T n I j because there's 4 of these. All right. Plus Q dot rho CP. All right. So that is the second 2D heat diffusivity, not diffusivity, heat diffusion equation. And in the next part, I am going to implement this in Excel. All right, so now I am going to model this equation. So first we're going to label T top, T bottom, T left, T right. Alright, so T top was 310 degrees Celsius. T bottom was, it was 215. Wait. $250. Left was 100 and right was 200. All right. So now we're gonna label equals T top. Or, I mean, no, sorry, T left. All right, and I'll go down 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. All right, equals T top 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Alright, equals t right, down 10, and equals t equals t bottom. Alright. So now we'll put the equation in, which is equal to above. Let's put above plus to the left plus to the bottom plus to the right. And then we divide that by 4 because it's an average. And enter. And we'll drag this across and down. There we go. That's it modeled.